In today's lesson, we're going to be looking at graphing polynomial functions. The purpose of this video is to give you an introduction to this problem and walk you through one example of it, and then in class we'll talk about more examples and answer any questions that you have about this process. So let's get started. When you're talking about polynomial functions, we always can revert back to the parent function as sort of a place to start. So the simplest polynomial functions that we've already dealt with are the three that you see here. We've got the linear function, which is right here. We've got the quadratic function right here, and the cubic function right here. And you can see again what the parent functions of those look like. What's interesting though is the quadratic function with its 2 as the, oh, that's a little dark, let me do that again. With that 2 as the exponent, that actually leads us to a more general situation where if any even exponent is on our x, we're going to get a graph that is similar to this. Probably something parabolic. It's going to behave very much in the same way as what the quadratic does. And similarly with the cubic, which we know is a third degree polynomial, really any polynomial with an odd degree is going to behave very much like what a cubic does, with that sort of S-curve to it in its most basic form. So that's something to keep in mind as we move forward here, is that x to an even power acts very much like a quadratic, and x raised to an odd power acts very much like a cubic. So when we're talking about graphs of polynomials, one of the characteristics we want to pay attention to is the end behavior. And the end behavior literally happens at the ends of the graph. It's what is happening when x gets really, really big or really, really small. So in something like our graphs here, what we're interested in is what's happening here on the ends. We don't really care so much about what's happening in the middle here. We're just interested in these ends. Okay? So, as you can see, get those out of the way again. We're still working with when is an even and when is an odd. So when is the exponent on our polynomial even? When is that exponent, that highest degree, going to be odd? And in this case, what we're looking at are situations where the a is positive. So that means that the leading coefficient out here in front of our highest degree term is going to be a positive number. So when we have a positive leading coefficient and then have an even or an odd exponent, we can expect the ends of our graphs to behave like the ends of these parent functions. So when it's an even exponent, then we would expect the ends to go up on both ends just like a quadratic does. When it's an odd exponent, then we would expect the left end to go down and the right end to go up, just like a cubic does. Now that's when that leading coefficient, that a, is positive. When it's negative, we know from previous lessons that having a negative a simply turns our graphs around. So now my parabola is going to look something like this, or now my cubic is going to look something like this. Okay, it reflects the original graph through the x-axis. So now, when I have an even exponent, I would expect my graph to follow what the quadratic is doing, but my quadratic is now going down on both ends. So an even exponent with a negative leading coefficient means both ends are going to go down. Whereas an odd exponent with a negative leading coefficient means that the left end is going to be the one that goes up and the right end will be the one to go down, just like a reflected cubic would. So if we can keep in mind these parent functions that we already know about, then we should be able to kind of visualize what's going to happen with different situations involving higher degrees. Now we can also look at the behavior of our graph at the x-intercepts. Excuse me. What happens here is that the behavior at the x-intercept will depend on how many times that particular zero got used. Or another way of saying that is, how many times did a particular factor get used in rewriting the polynomial? So if we end up with a factor that's been squared, that's really saying that that factor got used twice when the polynomial was being rewritten. So depending on how many times the zero is being used, that tells us what happens with the graph at the x-intercept. So if I just have a zero that was used once, then I'll end up with a graph that's just going to go straight through that x-axis. Now if I end up with a factor or a zero that was used twice or any even number of times, what that means is that that graph is just going to touch the x-axis. So we still have an intercept there, but it's not actually going through the x-axis. It's just coming down, touching that x-axis, and then turning back in the same direction that it came from. And if we have anything odd higher than 1, so a 3 or higher that's an odd number of times a zero's been used, then our behavior at the x-axis is going to look like a cubic. It's going to kind of come up and kind of flatten out and then go back up again. And so we're calling that flattening part right here a shelf. So there's really three things that can happen. We can have a graph that's going straight through at an x-intercept because the zero was only being used once. We can have a graph that touches at the x-intercept because our zero is being used an even number of times. Or we can have a graph that kind of flattens out at the x-intercept in a shelf because we had a zero being used an odd number of times, 3 or more. All right, so let's put all of this information together. We're looking at the function f of x equals x cubed plus x squared minus 4x minus 4. Now if you look back at the previous lesson, you will see that this is a problem that we've already worked on, and so we already know the factors. The factors to this function are going to be x plus 2, x minus 2, and x plus 1. And if you want more proof of that, you can look back at the previous lesson's online lesson to see how we got those. Now from those factors, that tells us that we have these three zeros. We have a negative 2, a positive 2, and a negative 1. Anytime we have real zeros from a polynomial, that is going to correspond with x-intercepts on the graph. So these three real zeros are telling us 3 x-intercepts that we can expect on the graph. We can also easily find a y-intercept by simply substituting 0 in for x, and we can find that to be a negative 4. So these are 4 very key points that we can now use on our graph. So here's our 3 x-intercepts at negative 2, negative 1, and 2. And here's our y-intercept at negative 4. Okay? Now, from there, once we have some key points, now we can start looking at behavior. So behavior at the x-intercepts depends on how many times each of these zeros got used. And in this case, each zero occurs only once. So we know at each of these zeros that we have, each of these x-intercepts that we have, the graph is going to go straight through. It's not going to touch, it's not going to do a shelf. We can also look at end behavior. Our leading coefficient in this case is a 1. 1 is positive. So we have a positive leading coefficient and we have an odd degree. That means the end behavior is going to act like a cubic. So we would expect that the left side is going to go down right here, and that the right side is going to go up right here. We don't really know what's going to happen in the middle, but that's okay. That's not what this pattern is telling us anyway. So now if we add that information to our graph, we know that our left side is supposed to go down, and we know that our right side is supposed to go up. We also know that the graph is supposed to go straight through at each of the x-intercepts, and it should go through the y-intercept. So if I start from here, I can come through this x-intercept, turn around, go back down through this one, come down to hit my y-intercept, and then continue on up so that I'm going through this x-intercept and continuing with my arrow going up. Okay, so putting all of our information together, the x-intercepts, the y-intercepts, the behavior of the graph at the x-intercepts, and the end behavior, we can put together a reasonable sketch of what our polynomial should look like. Now we'll talk about this more in class, and we'll go through a couple more examples then. So if there's anything about this lesson you didn't understand, please be ready to ask questions about it when we meet in class. And we'll see you then.